Hello everyone, welcome to the SQRT channel. In this video I'm going to talk about 9 problems from Singapore Maths Olympiad from 2005. These problems cover different topics from number theory, algebra and geometry. Let's focus on these problems now. In problem number 1 we have what is the unit digit of 7 to the power of 5. So basically if we calculate 7 to the power of 5, what is the digit that we are going to have for the rightmost one? Think about it and then we will talk about the solution. This problem is fairly easy if you know how to play with modular arithmetic. In modular arithmetic, we have a lot of rules, but let's start with the basic one. First of all, we need to find a number in a format of 7 to the power of something that if we calculate its mod over 10, then we have something that we can play with. Remember 7 to the power of 2 mod 10 is 9. And 9 mod 10 is basically negative 1. So I'm going to use 7 to the power of 2 mod 10 equals to negative 1. And then take power of 2 on both sides. I will end up with 7 to the power of 4 mod 10 is plus 1. And since we want 7 to the power of 5, not 7 to the power of 4, I'm going to multiply both sides by 7, and then you will end up with 7 to the power of 5 mod 10 is 7. So choice D is the answer here. Now let's focus on problem number 2. What is the value of 0.5 to the power of 3 plus 3 times 0.5 to the power of 2 times negative 1.5 plus 3 times 0.5 times negative 1.5 to the power of 2 and finally plus negative 1.5 to the power of 3. Think about it and we will see the answer in a bit. To solve this, you can initially start with calculating the algebraic expression that you have, but it's going to take time. But on the other hand, when you look at it, you can see that there is an identity here. I'm going to use a plus b to the power of 3 equals to a cubed plus 3a squared b plus 3ab squared plus b cubed. And a here is 0.5 and b here is negative 1.5. And obviously I'm going to end up with 0.5 minus 1.5 to the power of 3, which is negative 1 to the power of 3. And I'm going to end up with negative 1. So choice B here is the answer. Now let's move to problem number 3. What is the last 2 digits of 1 plus 2 plus 3 plus 4 up to 2005? Let's see how we are going to solve it now. Obviously one option is to start with finding what value we have for the first 2 digits of 1 and then 2 and then 3 and then for example for 2005 the last 2 digits of 0 and 5, and then we calculate those and then we add them together. Maybe you are going to start with that, but a better option is going to be calculating the whole number first because there is no uncertainty here. We have 1, 2, 3, 4 and up to 2005, and we already know that how to calculate the sum of numbers from 1 to n. I'm going to use that. I'm going to say I have 1, 2, 3 up to 2005. I need to add them together. We know that there is a formula for that, and the formula is basically n times n plus 1 over 2. Now based on that, I'm going to use 2005 times 2006 over 2, and as you can see the final answer is going to be 5015, and obviously the last 2 digits is 15. So here there is no number theory that I used. Maybe the questioner wanted to confuse you, but we didn't use modular arithmetic or anything like that in this problem. In problem number 4, we want to find the number of zeros that 50 times 49 times 48 times down to 1 end with. This is an interesting problem. Think about it. This is a common problem in different competitions, and I'm going to talk about that in a bit. To find the number of trailing zeros in a factorial, we need to find out how many times 10 is a factor of that factorial. So basically here we have n factorial, or in our case we have 50 factorial. We need to find how many times 10 is going to be a factor in this 50 factorial. To do this, what we are going to do is basically find how many times 2 is a factor, and then how many times 5 is a factor. Since we have 5 times 2, 10, and we know that 5 and 2 are prime numbers. Obviously, the number of factors that we have for 5 is going to be less than the number of factors that we are going to have for 2. So at the end, what I'm going to do is to find the number of times 5 is a factor of n factorial or 50 factorial that we have here. Putting everything together, I'm going to find the floor of 50 over 5 and the floor of 50 over 5 to the power of 2, and then I'm going to add them together. Here you are going to end up with 12 as the answer. So in problem number 5, we have a geometry problem. We have a square ABCD. We know that P is a point on the side BC in such a way that BP is 3 times PC. We know that Q is a midpoint of CD. Now we are given the area of the triangle PCQ. It's 5, and we want to find the area of the triangle QDA. Think about it and we will see the answer in a moment. To solve this, we are going to start with very simple things. So first of all, the area of ADQ is 1 over 2 AD times DQ, and assuming that we have A for AD, and since it's a square, we are going to end up with A squared over 4. Now for PCQ, the area is going to be 1 over 2 PC times CQ. And again, I'm going to use A for the side of the square. We are going to end up with A squared over 16. Now we know that PCQ area is 5. And because of that, I'm going to end up with finding A and then finding the area that I have for ADQ. Or I can say that from the two equations that you have, the area of ADQ is basically 4 times the area of PCQ, and if the area of PCQ is 5, the area of ADQ is going to be 20, and that's our answer. In problem number 6, we have the value of P which satisfy the equations P squared plus 9Q squared plus 3P minus PQ equals to 30 and P minus 5Q minus 8 equals to 0, may found by solving which of these equations that you are seeing here. Think about this problem. It's a little bit longer problem, but we are going to solve it in a moment. To solve this, first of all, it asks the value of P, not the value of the Q. So we need to keep P and ignore Q. To do that, I'm going to use the second equation and find Q, not P, and then I'm going to use the value that I have for Q in the first equation. That's the tricky part. So I have Q equals to 1 over 5 times P minus 8. And obviously for the first equation I need to find Q squared. So I'm going to find Q squared by taking power of 2 of what I have here. It's going to end up with 1 over 25 times P squared minus 16P plus 64. Now I also have PQ. So to do that, I'm going to find PQ, which is going to be 1 over 5 times P squared minus 8P. Now I need to replace these values in the original question number 1. Then I will end up with P squared plus 9 over 25 times the expression that you see here plus 3P minus 1 over 5 times the expression that you see here equals to 30. After doing some simplification, you're going to end up with P squared times 29 plus P times negative 29 plus negative 174 equals to 0, and then if you divide that by 29, you're going to end up with p squared minus p minus 6 is equal to 0, which is basically option A here in this problem. Now let's move to problem number 7. We have the digits 1, 2, 3, and 4. We're going to use each of these digits only once. We want to form a 4-digit number, and the problem asks how many of them are going to be divisible by 11. That's an interesting problem, so think about it and then let's see how we're going to solve it. The fact that I'm going to use here is basically divisible by 11 is going to lead to something very interesting. So let's say that we have a 4-digit number A, B, C, D. I'm going to expand it and write it as 1000 times A plus 100 times B plus 10 times C plus D. Now I want to find its mod 11 number. So to do that, first of all, I'm going to use -1 for 10. I'm going to use +1 for 100 because I know that 100 mod 11 is going to be 1. We know that 99 is 11 times 9. So I'm going to use that, and then for 1000 I'm going to use -1. So basically what you are going to see here is to find the remainder of A, B, C, D, I'm going to find what I have for -A plus B minus C plus D mod 11, and this number is going to be 0. So basically I need to find mod of -A plus B minus C plus D, and I need to have it 0. So let's see how we are going to solve it. To solve it, I'm going to start with using 1 for A. So let's assume that A is 1, and then I will have -1 plus B minus C plus D equals to 0. Now, to be able to use numbers 2, 3, and 4 and having this equation true, I need to use C equals to 4. Since 1 plus 4 is 5 equals to 2 plus 3 here. And remember, A and C have negative signs and B and D have positive signs. So you will end up with using 2 and 3 for B and D, but it doesn't matter if B is 2 or B is 3. The rest is going to come with that. So I'm going to move to the new case, which is basically A is going to be 2. A is going to be 2, so you can use the same reasoning and say that C needs to be 3. If that's the case, then B and D can be any number from 1 and 4. So basically for case number 1, where I have A equals to 1, I have 2 choices, and for case number 2, for A equals to 2, I have also 2 choices. Similarly, A can be 3. If A is going to be 3, then C is going to be 2, and B and D are going to be between 1 and 4. So 2 choices here, and for the last case where A is going to be 4, I also have 4 choices. So in total I have 8 choices, and that's our final answer. Now let's move to problem number 8. We have a polygon. We know that some of interior angles are less than 2005 degrees. We want to find the maximum number of sides that this polygon can have. Let's see how we are going to solve it. Here I'm going to assume that it's a regular polygon, and for this regular polygon, sum of the interior angles is going to be n minus 2 times 180 degrees if we have n sides. Now based on that, it's going to be less than 2005. Dividing this by 180 is going to result in n minus 2 needs to be less than 12, and then n is going to be less than 14, so n is going to be 13. Now problem number 9. What is the last 2 digits of 2005 plus 2005 to the power of 2 plus 2005 to the power of 3 and up to 2005 to the power of 2005? This problem can be the hardest among all those problems that we solve. Let's see how we are going to solve it now. I'm going to start with using 2005 to the power of n. So here we have n from 1 to 2005. We want to find the last two digits. So basically we are going to find mod 100. The first thing that I'm going to do is to see if I can generalize it and find what is going to be the remainder of 2005 to the power of n if I divide it by 100. First of all, 2005 is going to have 0 and 5 for the last two digits. So I'm going to replace 2005 to the power of n with 5 to the power of n mod 100. Now let's continue. We know that 5 to the power of 1 mod 100 is just 5. For 5 to the power of 2 we have 25, so mod 100 is going to be 25. Then we have 5 to the power of 3. It's going to be 125, and we know that the last two digits is just 25 or 5 to the power of 2. Now let's go and find what's going to happen if we have 5 to the power of 4. 5 to the power of 4 is going to be 5 to the power of 3 times 5. And we know that 5 to the power of 3 results in 5 to the power of 2 in mod 100. So replacing 5 to the power of 3 with 5 to the power of 2, I will end up with 5 to the power of 3 again, and then I can replace it with 5 to the power of 2 because we saw that the case. So together I have 5 to the power of 4 and 5 to the power of 2. They have the same remainder if I divide those by 100. And if you continue this way, you are going to see that 5 to the power of 5 mod 100 is 5 to the power of 2, 5 to the power of 6 mod 100 is going to be 5 to the power of 2, and so on and so forth. So basically I'm going to end up with 5 plus 25 plus 25 plus up to another 25, and the number of 25 that I have is going to be 2004. So I have 5 plus 2004 times 25, and I want to find its remainder if I divide it by 100. I'm going to replace 2004 with just 4 because it's the last two digits, and then adding and multiplying things together I'm going to end up with 105, which results in 5 or 0.5 if I divide it by 100. So I can say that the last two digits of the whole expression is going to be 0.5, and that's our final answer. Thanks for watching the video. Here we solved 9 problems from the Junior Olympiad of Singapore from 2005. I hope you enjoyed the content that I have in this video. Please let me know what you think.